Hopefully it's not too much racket going on. I know that's the primary thing on your mind right now, but there will be a lab this week on capacitance. And I think the first labs take place tomorrow. So at least divert some of your attention to that while possible. And homework 4 has been postponed till Friday. I think it's probably a good thing in many respects. It kind of synchronized things a bit with discussion. So Dinesh could talk about talk about capacitance during discussions. And you can ask questions about the homework if you have any. Alrighty. So today I just wanted to do a review, and it's been suggested by a few of you that I should just do some examples instead of just going over the concepts, and that's what I'll do. And recall a long time ago, we started out with the concept of forces, Coulomb's law, for point charges. So I'll start with that. Assumption here that you already are quite familiar with the concepts. Okay, hang on just a minute. I got something weird happening here. You guys see the next screen? The next slide, I mean?
Yes.
Okay.
Also, will these slides will be available too as well?
Well, that's the plan. I mean, it'll be like any other lecture. The lecture notes will be posted later in the afternoon.
Okay, thank you.
All righty, so let's consider this, the shown charge configuration. There's 3 charges, Q1, Q2, Q3, all on XY plane. The coordinates are given, they're shown here. In the parentheses, so where Q1 is located at the origin, Q2 is at X equals 3 meters, Y 4 meters, and for Q3 it lies on the X-axis, 4 meters away from Q1. So to find a distance from Q1 to Q2 will require triangulation. R12 is the sum of the squares of the differences in locations of Q1 and Q2. Hang on just a minute, it's weird on my side here. And so, what we have is, kind of a square of a 4. Wait, I don't know if this is showing up or not. Are you guys seeing some equations popping up?
For the R, yeah.
Yeah.
R1, okay. Something's a little delayed on this side. So the square of 4, 16, square of 3 is 9. So square root, I mean, some of that is 25, the square root of 25 is 5. Makes life a little easier here. And so we have one distance, Q2, it's 5 meters away, and to Q3 from Q1 is 4 meters. So we now have those distances, what we will need for coulombs.
Is that a typo? I think R12 is 5 meters, you said, right? Underneath the equation?
I should be right. Thank you for catching
Okay.
that.
Yep, you're welcome.
Yeah, that should be 1, 2. Yeah, thanks for that. And so now what we want to do is to determine the direction. And in order to do that, basically, we take the rise and run is what probably some of you heard of. But basically, it's the difference in the y direction divided by the difference in the x direction. Ratio of that equals tangent theta of this angle. Makes life easy, that being that Q1 is at the origin. And using your faithful calculator, you'll determine that to be 53.1 degrees. So we need to, what I'll do here is only assign some numerical numbers to the charge. It's all in microcoulombs. In the case of Q1 is plus 40, minus 60 microcoulombs for Q2, and for Q3 is minus 50 microcoulombs. So being that these two, and we really are not concerned with all the forces acting on Q2 or Q3. We're just making the assumption here that these are fixed in space. It's just really the concern of these two charges acting on Q1. And being that they're unlike charges with respect to Q1, we know the forces are attractive. So and that Q1 is toward Q3, for example, and the same for Q3. So we can look at this in the following way. It's a drawing of directions of F12 and F13. And of course, we can't just simply add the magnitudes together. We have to add this vectorially. So direction comes into place. And that's an easy task, you know, F13. It's all the magnitude lies in the x direction. But we have to decompose or dissect the components of F12 into its x and y components by just projecting the vector onto the associated either y-axis or x-axis, depending on which component you're most interested in. So like we've done before, what we'll do is just determine the magnitude of each force, F12 and F13. And that's what we'll do here in the next slide. Just copying over these figures for reference. And so just using coulombs in this case, and we're just looking at the magnitude. So we're just taking the magnitude of the, or just the absolute value of the charges. And we already know the distances. I saw given up in a figure above. And in the case for F, or at least R1, let's see, do I have an error there again? There's another error. It should be R12. That was just propagated over from the previous slide. So where it says R13 equals 5, that's incorrect. That should be R12. Everybody see that? Anybody there?
Yeah, and
Yep.
it's all.
All right, so R12 is 5 meters. So we'll just basically substitute the values for this. And K is 8.99 times 10 to the minus, 10 to the 9th, positive 9. You know, these, I should say, epsilon naught and K, that will be provided for you on the exam. So no reason to memorize. So substituting for that, we have these numbers to evaluate. And we'll go into details on that, but the end result is 0.86 newtons for this force between Q2 acting on Q1. Okay. And for the next force, Q3 acting on Q1, repeat the process, but of course we have a different distance to contend with. And one of the charges are different, Q3, slightly lower, but slightly closer. So who will win out? Well, actually, the distance will win out, being that it goes as a distance square. Evaluate the numbers like we did in the previous case, and we'll come up with a number slightly higher than the one for F12, and that'll be 1.1 newtons. Okay. Now, like I said before, we can't simply add the magnitudes to determine the resulting force, being that as a vector. You know, if these were scalars, it's a different story, but they're not. And so F12 and F13, they must first be resolved into its individual X and Y components. And that is what we'll do next. So this copying over the results of our magnitude calculation. And just breaking up in the table, you know, whatever method you want to use, you don't necessarily have to use this table method like I do. But okay, first what we'll start out is look at the X component. What is the X component of F12?
0.86 times cosine theta.
Yeah.
Yep, everybody agree with that? Main thing that is cosine. You're projecting onto the x-axis, and that is indeed a cosine. and a little bit more than a half a Newton in that case. All right, for the Y part, so you can just look at the chart above, the diagram above, and see this really need to substitute in for 53.1 degrees in theta, and this is what we have, and the number is a little bit higher, not about a lot, but it's 0.69 newtons. So for the other case, since the force as a result of Q3, and it lies on the x-axis, this is a pretty easy one to do. It is an angle associated with that. The angle is 0, being that the angle is respect to the x-axis. And cosine of 0 is 1, so the x component for F13 is 1.1 newtons. And of course, cosine of 0 is 0, so there's no projection onto the y-axis.
Question.
Sure.
On the exam on Wednesday, we wouldn't have to show that step for F13, right? We could just like write it as being in the X component entirely.
Yeah, I'm just being a little more systematic, probably more necessary. But yeah, it's entirely up to you, but you certainly wouldn't be counted against. It's saying it as 0. It is stated, like sine of 0, 0, but for the most part, you don't have to do all the, it doesn't have to be 100% explicit.
Cool, thank you.
I also have a question. I don't know if this is a dumb question, but can we assume that the charges will be given to us for all 3 charges on a question like this?
Well, yeah. If they're not, then the solution would be in terms of Q, 1, 2, and 3. You just wouldn't have a numerical result for it. But yeah, it's can't say for sure. I haven't finished the exam yet, but yeah, it's symbolic. If it's not, in other words, if the numbers aren't provided, then you're expected to follow through with the providing result symbolically in terms of Q1, Q2, and Q3.
Okay, thank you.
Yeah. Well, okay, now next what we'll do is sum these, the x component and y component separately. And for f of x, the x component of resulting force is 1.62 newtons. And for f as a y, it's a 0.69. No contribution from the force acting or charge 3 acting Q1. Charge 3 acting on charge 3 acting on charge 2, or charge 1, sorry. Trouble speaking today. Okay, so now we can construct the vector, the resulting vector from both forces, F21 and F31, or vice versa. And so we now just write this in the following way. Now, if we want to know what the magnitude of the resulting force is, how would we go about doing that?
Square the components and
Square
take square root.
Yeah.
Now, is this the quadrature?
No, I just meant to do like Pythagorean theorem, basically.
Well, I suppose you could, yeah. Yeah, that's the same thing implicitly, I guess it is. Think of it that way, yep. So the magnitude is just the sum of the squares of each component, and take the square root of that. So we can substitute in values now, and it turns out the length of that vector is 1.76 newtons.
Will you specify on the exam if you want the answer in unit vector notation or with a magnitude and an angle?
Well, yeah, actually we could have done this in the vector notation all the way through, as opposed to determining what the magnitude is. But either way, this is no incorrect way of doing this. I should not say that. There's an incorrect way, but I mean, there's, if you decide to do this, in terms of magnitude and direction, or just maintaining vector notation all the way through, either way is correct.
Cool, thank you.
Yeah. I mean, if any answer was correct, then, easy to grade. So now how would we determine the direction then?
You do the inverse tangent of the y component over the x component.
Exactly, yep. So tangent of that direction, I guess in this case, respect to the x-axis, is the ratio of the y component of the force divided by the x component. And from this, make the substitution. And voila, 23.1 degrees. Not too surprising, being that the force as a result of Q2 is at 53 degrees, and this, it's basically toward that location. And the other force is at a lower angle, it's at 0 angle, so you would expect it to be somewhere in between. And that's what we get here. Maybe not necessarily halfway, but somewhere in between. It's a good way to check your result. So any questions about that? Certainly should expect a problem similar to this on the exam. And I'll make sure that the charges will have numbers associated with it. All right, no more questions. I want to now talk about electric flux a bit. A couple of examples. All right, so we have electric field in region space shown around this box. It is given by this vector where the electric field is equal 8 times the unit vector x, or I, plus 2 times the unit vector j, which is in the y direction. And units is in Newton coulombs. It's uniform, obviously, because there's no spatial dependence on this vector. It's that vector anywhere in space, x, y, z, regardless what it is. That magnitude, that direction is unchanged. And so what the question is what is the magnitude of the electric flux through the top face of the cube shown below here? Remember, the electric flux is the sum of the dot product electric field into a unit area element. We'll call it dA. It's breaking up the area, in this case on the top face, to many pieces. And we know as a result of it being a flat part, I mean, it's just flat in space, it's like a plane, that dA always points upward. Notice the integral is shown here. It doesn't have a circle on it because it's not a closed surface. We're only concerned with the top face of this cube. And as I already pointed out, electric field is the same magnitude and direction everywhere in space, and most importantly on the top face of this cube. All right. And since the top face is flat, as I already stated, all the area elements, dA, point in the same direction, which is in the positive y direction. So we can rewrite this all the area elements on the top is equal to dA in the y direction, j hat. Everybody okay with that? All right, for the flux through one of these area elements, dA, I'm calling d phi sub e, is equal to the electric field dot into dAt. A, this is T, this represents the area element on the top surface. And so we just dot these. I'm sure most of you guys are familiar with dot products, right? Vectors. I mean, I know you are to a certain extent, but with explicit components.
We did that in 207.
Okay, good. So you can see here then, when we dot dA sub t, into this vector, a sub I plus j a times I plus 2 in the y direction. The only thing that survives is the j part, the y direction of the electric field. Consequently, you end up with this relationship for the at least for the flux from some area element dA somewhere on this top surface. The contribution in the x direction does not contribute. Okay, so let's have full flux across the surface of the top face. We have to integrate over the full area. And we've already determined the dot product. And that's the same over a whole surface. So we can pull out the electric field component out of the integral because we know that's constant. And just integrate over the surface. And the surface of a square, which is the shape of the top face, is 3 meters times 3 meters. That's the size is shown here. And so that's 9 meters squared. So the end result for this given case, the flux through that top surface for this particular electric field is 18 Newton meter squared per Coulomb.
Can I ask why DAT is only in the positive y?
Remember, dA is in a direction that's perpendicular to the surface. And given that it's, let's see, it's a closed surface, and it's by definition, we've always said that, well, dA is like going outward from the closed surface. So that's why, I guess theoretically, I could have said it's, it's either in the negative direction or a positive direction. But, being that this lies, in the XZ plane, if you want to think of it that way, the perpendicular to that is in the Y direction. That's how dA is, the direction is defined. Does that make sense?
Yes, thank you.
So how would things change if I were to say, well, let's take the case where I don't have it labeled, but it's like one of the sides of the cube. Let's say
the X component
in the ZY plane, such that the vector direction that describes the area elements on that surface points in the positive X direction. Would that change our result? For the same electric field that's shown here.
Did you mean like the like when you say ZY here, the Z is what's going into and out of the screen, right? For this example.
I don't know if you can see this diagram is kind of small. Maybe it's a problem. But yeah, Z, based on this drawing, is like coming out of the page. Can you see my mouse moving?
Yeah.
Okay, so in this direction, and X is to the right, Y is in the upward direction. And so what I mean by in the YX plane, let's say this surface here, for example.
The value of our answer wouldn't change.
What's that?
Actually, wouldn't the value change because this time the the component of the electric field that is
Oh, it is
parallel
eight,
to the
yeah.
DA is going to be the 8 instead of the 2.
Now it's gonna be 8 times 9, 72.
That's exactly right.
Yeah, good catch.
Well, your area is the same, being that it's a cube by definition. So the area is 9 meters squared. But instead of multiplying it times 2, we're multiplying it times 8, right? So we get a different result, 72, I guess, right?
And this would be if it was the rightmost face.
Yeah, actually, it would not matter. I mean, I suppose if you wanted to define the area element to be outward, from inside out, that face would definitely be positive. The other side, let's say, is closer to the origin, I guess. You would get a negative result. The magnitude would be the same, but it would be a negative 72.
For a problem like this, would we be given, instead of vector notation for the electric field, would we be given a magnitude and an angle measurement for how
Well,
the
you
electric field is
could,
there?
but you can determine that either way. I thought this would be easier because you don't, I mean, here you can explicitly do the dot product. And, being that the faces are aligned with, one of the axes, how's dot defined here. But the other way would require a few more steps, I would believe. So I would probably have it in this kind of notation, just because I think it reduces the amount of math. But I mean, you could convert it to that if you wanted. I mean, it's just the magnitude, it's this square of x component and plus the square of the y component, square root that. And then to determine the angle, it would be like tangent theta over would equal to 1/4, right? So the conversion, I mean, you could go back and forth for each, at least for two-dimensional vector. Any more questions? I need to move on here. I got a lot of examples to do. Let's just move on to this next one. You have seen this one. So let's say you have a electrofluxometer, and you were able to measure the electric flux on all 6 sides of a cube. You want to know, what is the net charge inside this cube without opening up. And here I have a list of the data that you took. So phi 1, that's the flux that you measured on the face that's closest to you. In the case for the flux 2, it's on the right-hand side. And flux 3 is on the back side, not visible to us. 4 here is actually not visible because the way the cube is tilted. And 5 is on the top, and 6 is on the bottom. So how would you go about doing this? You have the total flux. Some of it's going in, some of it's going out. You have some, maybe not, very likely you'll have some charge configuration inside, but really doesn't matter. Because Gauss's law, for example, it's not dependent on really that sort of geometry. I mean, it's just really, it's correct everywhere. Utilizing it, to solve problems, you need symmetry to really take advantage of it, but Gauss's law is correct everywhere in space. So how would you go about solving this?
Just add them up and set it equal to Q over E naught.
Yeah,
Exactly.
cube closed.
So the total flux enclosed is equal to this integral, but really unnecessary to look at the electric field because we've already measured the flux. And it's really, it kind of bypasses this integration. I mean, if we were given the electric field, it's a different story. We're given the flux explicitly, and that is equal to the amount of charge inside, enclosed, divided by epsilon naught. So do exactly what I was told. Just add all the fluxes together, and these numbers. This is basically what I have here on the left. And by doing so, we get -6 Newton meters squared per Coulomb. So it appears to be a non-zero flux, indicating there is a net charge inside. And therefore, just basically multiplying both sides of this equation by epsilon naught, we have this relationship. And I just brought it out in terms of epsilon naught. It's a small number, obviously, because of the magnitude of epsilon naught is, the order of 10 to the minus 11, or 8.85 times 10 to the minus 12. Okay, does anybody have a question on this?
What was your final value that you found?
What is the final value of what?
Like, what was the net charge that was found?
It's -6 times epsilon naught coulombs.
Wouldn't it be divided by epsilon naught? Because in the original equation, it's Q inside divided by epsilon naught.
Well, if you take this equation, Gauss's law here at the top, I don't know if you can see my mouse moving. Let's see here. You guys see the mouse
Yes.
cursor move? Yeah. So our goal is to determine the charge inside. So we need to multiply epsilon naught by both sides.
Oh, I see. Thank you.
Yeah. So if you wanted to get a numerical value of this, you would need to multiply -6 times 8.85 times the minus 12. I mean, if you want to give a solution like this on the exam, that's perfectly fine. This is up to you. Any other questions? All right. I mean, it will be, after this lecture, there'll be office hours until 3:30. So you have me cornered for a long time. All right, so let's go on to the next example. You guys seen this fairly recently. So we have an insulating charge, a solid sphere of radius A, and it has a uniform volume charge density, rho. And this is a positive charge. This is uniformly distributed within this volume. And what we want to do first is to calculate the electric field at a point outside of this sphere. And because the charge is distributed uniformly throughout the sphere, the charge distribution has spherical symmetry. So we can apply Gauss's law to find the electric field. And of course, to reflect the spherical symmetry, the best type of surface to use is a spherical surface. And that's what you can see here is drawn. Okay, and of course it should be concentric with the charged sphere as well, such that the electric field emanating or passing through the Gaussian surface is perpendicular everywhere. In other words, if E dot dA is equal to EdA. All right, so let's write this out here. Gauss's law. For this, just remember this integration, this integral of the circle, this means just a closed surface. And being that the electric field is emanating or passing through this Gaussian surface everywhere, being that the Gaussian sphere is concentric with the charge sphere, will be perpendicular at all points. And so the dot product goes away. It really goes away, it just goes to 1. It's 1 everywhere. And this must equal to the total charge in this volume divided by epsilon naught. All right, so we can bring out the electric field, being that it's constant everywhere. Remember, on this surface, must be constant. As if like all the charge is concentrated at the center, at least that's what the electric field, it gives, it is equivalent to that. And so we can basically pull out electric field out of this integration. And so integrating over the surface of the sphere is 4 pi r squared. And again, that must be equal to the enclosed charge within the Gaussian surface, which is the full charge. And now we can solve for the electric field. We get this relationship. Again, this is a field is identical to that of a point charge. But that only works in a situation if the charge is uniformly distributed, within the volume. How would this change if this was a conductor? Would the result be any different? If we were to somehow, just for some instant amount of time, uniformly distribute the charge within a conductor, a spherical conductor, what would happen?
Wouldn't it be the same because the charge inside is still the same?
Exactly right. But one difference is that all the charge would move to the surface very quickly.
So the difference between the insulating solid sphere and a conducting one, it would only matter if you're checking the electric field within the sphere?
Exactly right. Inside the sphere, there would be no enclosed charge for a conductor, but for an insulating solid sphere, the charge just stays where it is. It's not able to move around. That's the difference.
Okay, gotcha.
Yeah. So on that subject, let's look at the electric field inside the sphere. So in this case, again, we'll choose a Gaussian surface, but having the radius r in this case, this is r is the radius of the Gaussian surface, is now less than the radius of the charged sphere. Again, it's concentric with the insulating sphere. Okay, and so, but now it's important that we define this quantity rho. In the previous example, it's not really crucial, but here we defined it, which is the total amount of charge that's deposited onto this sphere divided by its volume. Okay. So the charge inside is what we're interested in. The charge inside this Gaussian surface is the only part that contributes to the electric field inside the charge sphere. And that's as a result of, well, actually something we showed brute force mathematically using coulombs a long time ago. But now we can just use Gauss's law. And so the amount of charge enclosed, being that the charge is uniformly distributed, it's just rho times the volume in which we are enclosed as a result of our Gaussian surface. So this is a relationship between my charge enclosed and the size of our radius of our Gaussian surface.
Is that the same thing as like big Q times R cubed over A cubed?
You can do that, yeah, if you make the substitution in for rho, yeah. Exactly. Mm-hmm. All right, so now let's look at Gauss's law, or at least look at the flux. Same situation, recall, like everything outside of this, all the charge outside of this Gaussian sphere does not contribute to the electric field. So, we can ignore that. But still, the amount of charge inside, it still has, spherical symmetry. And, consequently, the direction electric field is outward, perpendicular to surface everywhere. So again, we can pull out the electric field from this integration. Okay, and the magnitude is the same as well. So dA is integrated. Let me see. Sorry, my mouse is on the wrong screen. So we integrate dA, and it becomes 4 pi r squared. Of course, that equals to the charge enclosed inside divided by epsilon naught. So now we just solve for the electric field. We can now substitute in back for rho, 4/3 pi r cubed. And that's what we'll do here. Numerator is not really changed. I just shuffled around epsilon naught because we know this is equal to k. K sub e is equal to 1/4 pi epsilon naught. So this basically simplifies quite a bit, and this is equal to rho, the volume density times r divided by 3 times epsilon naught. And if we want to get back this in terms of charge, the total charge, that's what I'll do here. We write this in the following way. Rho is substituted back in. And now we have this relationship. So the electric field is linear respect to r. So closer you are to the center of the charged sphere, the smaller r is. Smaller the electric field is. And once r is equal to 0 in this case, the electric field is 0. But that makes perfect sense. Is that your Gaussian surface then encloses 0 amount of charge at r equals 0. So it is consistent. Oof, running out of time. Okay, so let's just want to look at both equations and evaluate them at the surface. Hopefully they give us the same result. Always good. I mean, mathematics is the language to the universe. So just interpreting math correctly. I mean, I would never say that to a mathematician, but I think it is true. So in the case for outside of the sphere, for r greater than a, we evaluated at a, and we get this following relationship. So let's look at the other one, at least for the electric field inside, and yes, we end up with the same result. So that's good. Got an interesting discontinuity here too, but it's fine. That's to be expected.
Question.
Yeah.
If we were given this problem, but would there be a case where instead of using Gauss's law to solve it, just solve it as if it were a charge distribution and do the whole rho dv kind of a thing?
Yeah, there's multiple ways of solving this. It's, as long as it's using principles that's consistent with this course, yeah, that'd be fine. But yes, just applying your understanding of the concepts is what we're evaluating.
Cool. And then also, these questions that we went over in class today, do they approximate the difficulty of the exam questions?
Yes.
Cool. Thank you.
Mm-hmm. Okay, now, so what we want to do is take this result and determine the electric potential of a uniform solid. This is something we've done recently, but I just thought it'd be worthwhile to look at this. In case there's questions, this is now the opportunity to ask. So basically, we're going to take these same results and now find the electric potential of the uniform charged solid sphere, insulator. So that's what we'll do. And like we did before, we'll integrate out to infinity. Do this to be consistent with what we have done in the past. But we'll use the results from the previous problem for determining this electric field is something we've already calculated. No reason to calculate it again. So recall this for R greater, now our sphere is, it's not A, but it's big R. Sorry about that. So the electric field is given in the following way, which is KQ divided by R squared. And so now to determine electric potential at some point outside the sphere, we have to do the integration from infinity. Well, I guess we could, I guess all the way to R if we want to do all the way, if we want to go all the way to the surface of R. So do this integration. I mean, this is something we have done. And by the way, I will not provide integral tables because the only integrals that you'll be needing to do is things that you should have learned in 241, like integration, like 1 over R squared, I think is something you're very familiar with, or a linear, in case if you had to, like the next situation here, if you had to integrate a linear function, I would expect you'd be able to do that. In other words, just don't expect a, I mean, if there is like an integration that's somewhat complex, what I will ask is, well, just set up the integral. Don't solve it. But this is something you should be able to solve. And actually, I kind of fudged here on the limits. I should have put this like R prime or something here, because it's always kind of weird if you're integrating over R, but you really want to integrate, or you want to evaluate it at some distance R. I mean, this little R is just used too frequently. I probably should change this before posting it, but I don't know. You guys see the problem here? I just have too many R's.
Make one a dummy variable.
Yeah, I mean, I guess I could have used DS as opposed to DR in the integration. But yeah. But yeah, this is kind of a, I would say almost impolite to do this. So I'll fix this ahead of time. I just needed a dummy variable, and big R was not a good choice. So, all right, but anyhow, this relationship between the potential anywhere in space outside of this sphere will go as KQ, where Q is the total amount of charge on this sphere divided by your distance from the center of the sphere. And where this distance is greater than big R, the radius of the sphere. This is pretty straightforward, I think. So now let's look at the case inside. We've already determined that relationship between the electric field and the distance away from the center of the charged sphere. So now we're inside, something we have just derived. And so now what we want to do is determine the electric potential somewhere inside. Now, remember, we have to do this piecewise because the electric field, the dependence on the spatial dependence depends, whether or not you're inside. I mean, the form of the dependence, it's whether you're inside the sphere or outside the sphere. And so it's not a simple smooth function all the way out to, for somewhere inside the sphere to some very far away distance. And so we have to do this integration, what I call piecewise. This is because the function or relationship changes as you cross the boundary of little r equal big R. And so let's wrote this in terms of the electric field. Outside, integrating that from infinity to the surface, big R. And then once we're at that surface, we want to integrate the form of the relationship of the electric field inside. So just substituting in for these two forms of the electric field. And actually, the one on the left is something we already have just done. You can just substitute in KQ divided by R. And this is just a linear relationship. So the integration of a linear function just goes to the power of 2. So that's something I'm confident you guys should be able to do. So this is the relationship here. So evaluating this integrand from infinity to R, big R, we now have this relationship on the left. So we're now at the surface, and now we want to go inside the volume. And in that case, we have to evaluate that integrand from big R to the location of where we are inside. And as a result, we have this relationship here. Is everybody okay with that?
I have a question.
Yeah, sure.
If you know that the relationship between electric potential is KQ over R, do you have to, like on an exam, go through the actual integration, or can you just evaluate it as KQ?
Yeah, I mean, if you
over
already did it like previously, if I'm asking for the potential outside, let's say, yeah, you say you can just use that result. I mean, this is like your integrand that you're evaluating. So you could just explicitly write that down, but you might want to state in words where you got it. But yeah, that'll be fine. So I just want to simplify this a little bit more. You can see, like, if you were to bring out this R squared term and multiply times this factor, you have a similar term as it is on the far left. Combining these two, now you have this relationship. I don't know if you can see where I got that, but you can do the algebra. Okay, so the question I have now to you, what is the potential difference between R, little r, at 0 and little r at the surface? How would I determine that? But, just on this relationship that we determined, how would we calculate that? This is based on what we have so far.
Can you restate that? Like you said, little r at 0. What do you mean by that?
Oh, well, you're right at the center. You say your location, little r just represents your location with respect to the center of the sphere, the charged sphere. And if your location is, and if you're at the center of that sphere, little r is equal to 0. Right?
Yeah.
And if you're right at the surface, then little r equals big R.